parallel languages. Philips was a partner, and there was a special working group on the semantics and proof theory. It was led by Jacob de Bakker at that time. And I was responsible for the development of this proof theory of the language called POOL. It was developed by Pierre America, a parallel object-oriented language. So that was very interesting. I think they were not so lucky in their names, or the names actually were kind of faithful because the implementation was called Doom. Where it's behind glasses and at least you can look at it. But it was an interesting project. At least it provided me with a doctoral degree and thesis. Okay, my talk is about runtime assertion checking of Java programs. This is work by me, Frank, and Stijn. Usually I should say first the other and then, but you guess why I call it Frankenstein. But it's Stijn de Gouw, who's a former PhD student of mine, so currently a postdoc. And together we developed this theory, and Stijn did the main work on the implementation. But before I want to talk about this, I want briefly to show you something about which I'm very happy, to say a bit even proud. This is a recent work, so it's kind of advertisement, so excuse me for this advertisement. I think it's also relevant in this context because about this work, I'll tell you a few seconds, a few words about this work, but we developed a blog post about this work, and it has been a tremendous impact, at least according to my expectations. So this blog post has got 216,000 reads by now. We got a lot of positive reactions, not only from our community, the formal methods community, but I'm also very happy to say that we got a lot of very positive reactions from developers community, which seem now to embrace formal methods, like, wow, what did these guys do? Where can I find this method? How can I use it? So it was really very nice. So what we did with Stijn, we looked at correctness of certain sorting algorithms. Now that worked out fine. Mechanized proof, we published them as so-called proof pearls. I don't remember which journal actually it was, but then at some point we came across this TimSort thing, and which is a well-known sorting algorithm which merges, combines merge sort and insertion sort. And it's used in like the Java library, but also in Android and in Python. And so we wanted to prove it correct, but we didn't succeed with it. And we found a bug, but bug sounds like a trivial minor thing, but I can say it's really an error in the functional design, so to speak, of the algorithm itself. There is a basic invariant which simply does not hold. As a consequence, certain bounds are not respected, and therefore, for certain kinds of inputs, the whole program crashes. So if you are interested, I mean, you can, I invite you to have a look, but now I have the problem to return back to my, to my presentation. And there we are. Very good. So, yeah, the message, formal methods matter. That was the justification of this small detour. So, but what I'm going to talk about, so let's go back. In this way, I don't proceed really, but Chair, don't worry, I will progress through the slides. So let's go back to the title. So the main target is to extend runtime assertion checking in such a manner that we can specify both data and so-called protocol-oriented properties of Java programs. And by the very nature of assertions are state-based. Yeah, so they talk about relations between the program variables. While protocols, yeah, different kind of species, animals. Yeah. So what are protocols? Yeah, very abstractly speaking, a protocol is a sequence of interactions, also known in the literature as history or traces. And there's really a huge amount of literature about these notions, because they form the formal foundation of actually concurrency for compositional and fully abstract semantics for concurrent systems. One in general needs a certain form of histories and traces, like developed by Brooks, Hoare, and Roscoe for CSP-like languages. But for example, it played also an important role for the formal justification of proof systems for concurrency, like for CSP. There you have a proof system developed by Abt, Heuvel, Francis, which in itself does not use histories, but involves a kind of cooperation test. But for proving completeness, one needs to define histories. What I want to focus on is this particular work. It's already by now 2005, but okay, consider it recent with respect to the other works. So Jeffrey and Radke, they developed a fully abstract trace semantics for a core Java language. And this is somewhat surprising, because the core Java language is purely sequential. Well, the main notion of traces and histories have been developed in the context of concurrency. What do we see here? That traces apparently also are needed to obtain fully abstract semantics for a sequential subset of Java. Well, if you look at this core language, it's the core of this core language is actually a procedural language, a simple sequential procedural language. And as such, the standard input-output semantics should be sufficient as a basis for a compositional description. However, in Java, it's not just procedures. This core language does not only support procedural abstraction, but we have additionally the abstraction as provided by classes. So you don't have only procedures, but actually you group procedures into classes, or you may see actually classes as a kind of module. And this additionally structuring mechanism actually requires, for a full abstract semantics, these traces. So in a way, one can say that object orientation is already inherently parallel. So even if you want to describe by assertions Java programs, you actually would need already traces. And again, like the motivation of this talk was, assertions by their very nature are state-based. So how can we still use assertions for example, describing contracts? Where a contract, for example, of an interface, ideally should abstract from the internal implementation. But the internal implementation is given in terms of the state. So if there is no state, so what would be your pre and post conditions of the methods? That's a simple problem, and the state of the art, very roughly, there's of course much more to it, but in practice people say, we abstract from the state by introducing getters or model variables. This is basically beating about the bush. I mean, in the end, you have to define these getters. They are defined in terms of an internal implementation, and the same applies for these model variables. So this is really not a systematic approach for describing interfaces in terms of contracts which abstract from the internal implementation. So that's the goal. And the idea is very simple. but I believe in practice rather effective. So it's not just the idea, I want to say, but it's also the actual tooling, the implementation. That's important because I think one of the formal methods which are easy to use in practice is actually that of runtime assertion checking. If your assertions, if the abstraction level of the assertions coincide with the programming language, then you can safely assume that programmers, developers can use assertions themselves. Of course, if then one wants to verify them, for example, as we did for the stem sort algorithm, which we verified using the key theorem prover, that's a different story. You need to be an expert in theorem proving. But for runtime checking of your assertions, it's just push button. So it's a very easy, natural, formal method to be used in practice. Unfortunately, there are some problems also, not only with respect to this more conceptual problem, so how we can specify protocol-oriented properties, but the problem is also in the tooling. So a state-of-the-art framework for specifying contracts is JML, Java Modeling Language. And for the tooling, there are really quite some problems, like compatibility with new versions of Java. I have some contacts with people in industry which were, still are, very much interested in using this runtime assertion checking, but they simply got disappointed because with the existing tools they couldn't apply to their Java programs, which are written in versions which are not supported. So already in the tooling there is really also still a lot to be done. But here I want just first briefly go through the basic idea in terms of a running example. Yeah, the classic example of a stack. So I have an interface of a stack with two methods, operations methods as they are called in Java. A push method with a parameter item of type object, and I have a pop method which returns a value of type object. So the question now is, how can I specify, for example, by means of pre and post conditions, these push and pop methods? But I don't know anything about the internal implementation. And I also don't want to know anything about it. Actually, I want to specify it so that I can, at runtime, check these assertions for any given implementation. So the modeling framework, the basic idea is to use attribute grammars. So I will now explain briefly, step by step, how we use attribute grammars for specifying, say, behavioral interfaces. So the first notion of the modeling framework is message types. So with such an interface like this, automatically comes a certain number of message types. For each method, you have a call and a return. But additionally, for example, for a call push, this can be seen as a class, as an object. We have certain attributes. And for each method, we have as attributes simply its parameters. So we have as parameter, or say as a field, an attribute called item of type object. For the return push, this is a void method, so we don't have any attributes. For the call pop, we don't have any parameters, so it does not have any attributes. And for the return pop, so it returns an object, and that is described by this attribute. So message type go together with an interface, or an interface generates a finite number of message types like this. And basically the idea is that these messages contain attributes. For example, the parameters are introduced here as attributes and return values. So the next, if you want to use this framework, you can specify, for example, for this interface, the stack interface, what we call a view. And in the view, you just identify these events which are of interest. Because, as we will see later, for specifying the stack, I need only to specify these events, the return push and the return pop. The call push and, well, is that right? No, we'll see later. I claim now that for the specification of the stack, apparently only these events are relevant. The return push and the return pop. So in general, in a view, the user can just specify these events which he thinks or she thinks are of interest. And he introduces his or her own names. These names actually will be used as tokens in the grammar, as you will see in the next slide. So this now shows the use of the attribute grammar, in specifying this interface stack without referring to any internal implementation. So the behavior of a stack is simply specified by this grammar, which roughly generates all sequences of pushes and pops, such that the number of pushes is all, for every prefix is always greater or equal than the number of pops. That's roughly the idea. So this is a standard grammar, but this is the extension with attributes. I mean, I'm not going into the details of the definition as provided by Knut of attribute grammars, but roughly it works like this. So here I can define my data structure. In this case, it's a list, an extension actually of the list as provided by Java, with a prepend operation, and which is overloaded for an element and for a list. So what is the basic idea? So for this application of this grammar rule, I update this attribute stack, so which is a list in Java, by basically just pushing the element, so which is sent as parameter implicitly. So, but this is a token which has as field this item. So I can use this notation, and this then intuitively means that I push this item onto this stack, this list. And if I have a composition, a concatenation of two, if S goes from S1 to S2, then I basically just prepend the second one to the first one. And in the case I have a balance sequence, I just clear the stack. The stack becomes empty. So this is a simple attribute grammar, which actually generates from a sequence of pushes and pops, just the elements which are stored in the stack. And this stack is represented by this list. That's the basic idea. So this attribute is just an abstraction of the history. And now, okay, I will skip this. I think it's obvious. So here I show how these attributes then can be used in pre and post conditions of this interface stack. And so I don't have an internal implementation, but I have now this attribute grammar which defines this attribute stack, which is basically just a list of elements stored in the stack. And this I can now use, I can talk about in the pre and post conditions of the push and the pop methods. This is JML syntax. It's a bit verbose, but the idea is that here's the push method, and we have here the ensures, so that's the post condition. So given a class which in a way implements my view, which is called stack history, it goes standard in this modeling framework that can introduce a kind of model instance variable of that type. And I can refer to the attribute as defined by the attribute grammar. So actually the history is a representation of the attribute grammar in the Java language. So, and I can refer to the attributes defined in this grammar by simply saying history.stack. Then I obtain this, the value of this attribute as generated by this grammar. And basically as post condition, I then simply can state that if I push something, then the current stack, so at the end of the push operation, is just the old one plus the new element added. And similarly for the pop, I can add as precondition the requirement that the stack is not empty. So history.stack.size is non-empty. And furthermore, I can obtain the result. I can define the result as just the head of the stack, and the remaining part is just the tail. So I basically just described the pre and post conditions in terms of the usual head and tail operations of this attribute defined by this attribute grammar. And so I get an interface specification of a stack, which I can check at runtime for any given implementation. So how does that work in practice? So this is a summary of the modeling framework. So you have an interface specification, then you introduce this view, you identify the events which are relevant, then you introduce an attribute grammar, which defines basically the attributes, which are certain abstractions, so to speak, of the history of this interface. And these attributes then can be used in the pre and post conditions in a JML manner. So this has been integrated into this JML framework. So this is a sequence diagram of how it goes behind the scenes, but I'm a bit running out of time, so let me focus just on the overall tool architecture. So this has been developed by Stijn de Gouw. So what is given? So at design time, at the design stage, so you come up with an interface which specifies your methods, which can be implemented by certain classes. Then you describe, you introduce the view, you specify which events are of interest. Then you specify the attribute grammar, and then you have this mechanism of the JML asserts. All this will be fed into a meta-programming environment that is given by RESCO, which has been developed originally by Paul Clint at the CWI. It was called an ASF, SDF or something like that. And this latest version is Rascal. So what it allows you to translate your program in such a way that whenever you evaluate a precondition, automatically the attribute grammar as being, for the attribute grammar, there will be a parser generated. So when I evaluate the precondition, I will trigger this parser, which will parse the sequence of events, which will be stored in an extension of the program, like for example in a history variable. So this parser will generate new values of attributes, and these attributes then can just simply be evaluated by the JML asserts. So this is a very nice integration, because in itself JML doesn't know anything about all this. Doesn't know that behind the scenes there's an attribute grammar, there's a parser generator, and that before a precondition is evaluated, the attributes are being evaluated by the parser. So that yeah, a few minutes. So the Java features which are covered by this includes constructors, dynamic binding, polymorphism, inheritance, method overloading, static methods, and more importantly, also multi-threading. So you can show that in this framework, you don't have the usual problem of interference, because if you have in general assertions, runtime assertion checking for multi-threading is a non-trivial issue, because in principle one would have to freeze the whole state in order to evaluate such an assertion in the presence of many more threads. But in this setting, this can be dealt with in a rather easy manner. The tool can be found on this website. So summarizing, what I claim is that this approach of using attribute grammars for specifying abstractions of a history, which does allow you to specify an interface independent of an internal implementation, is a very nice one, because it's a declarative way of specifying these properties of histories, which can be also seamlessly integrated into JML, or for that matter, in any tool which supports runtime assertion checking. Currently, we are developing an extension of this framework for monitoring cloud applications. That's in the context of an FP7 project, a physics project, where there's one industrial partner on e-commerce which provides its software as a service on the cloud, and which are very much interested in monitoring those cloud applications for compliance with SLAs. So the details of what I have described so far can be found in these papers. So I should emphasize here that, for example, in this paper, you have seen just as a running example the stack, but we applied this to an industrial case study as provided by one of our industrial partners. And this was published in this aspect-oriented software development because one technique for generating a program such that it records histories, you can of course add an auxiliary variable and update each time when you do a method call. You can update this history variable, but syntactically can be quite a mess because of how method calls can be nested in arbitrary expressions. So a much nicer approach is that of expect orientation. And that ends my talk.
Okay. So thank you very much. Are there any questions?
Crisp or clear or completely confusing?
I'm just wondering, you check pre-post condition and invariance, I suppose, of the classes. Do you also check some temporal? No, actually, we clearly wanted now temporal in the sense of the abstractions as provided by the attribute grammar. The attributes are certain abstractions of the history, and there the protocol aspects are expressed. But we wanted to avoid at all costs, because there are extensions of JML, for example, with temporal logic for dealing explicitly with events and their ordering. But I don't think we should pester developers too much in imposing all kinds of difficult frameworks and try to have it as easy as possible. That's why we advocate this approach.
So this monitoring framework, there are properties that you may want to enforce at object level and at class levels, right?
Yeah.
You can handle both of them?
Yes. In principle, you could, I have to think a little bit about that. In principle, at the class level, you could, for example, project a history on a certain object, and then introduce that object actually as an abstraction of the history, and then specify properties of that. But in principle, this can also apply not only to a class, but also of the overall behavior of a system. I focused here very much on class and interface, but it could also be applied in specifying the overall behavior of a system.
Okay, thank you very much. Yeah. Hi, good to see you. Sorry. I'm very happy to introduce the next speaker today, Wayne Look from Imperial College.
Thank you very much. It's a great pleasure to be here. So I'll talk about assertions for hardware, which is a recent research area that we've been involved in. So quick outline of the talk. My focus on hardware is on hardware that can be programmable. So what are the challenges for such hardware design? And then I'll introduce some work that we are doing on how to provide a means of monitoring the execution of user designs, but minimizing the resources and the effects on the user design. And then I'll talk about how this could be achieved using this idea of in-circle assertions and exceptions. And then I'll introduce two kinds of assertions. One is temporal assertions, and I'll give an example of how the implementation of those assertions can be optimized and verified. And then I'll introduce something perhaps less familiar, which is the statistical assertions, and then a quick summary. So of course, there are lots of people to acknowledge. Team Imperial, Stefan, who's at Airbus, who gave us a lot of good ideas from industry, Mary Sheeran and Karen Jones, who introduced me to Ruby, which I'll mention briefly today, and of course, Tony and Jifeng and Jeffrey Brown, who allowed me to work, supported partially by the ProCoS US project, which resulted in some very interesting designs. And then there were some European project funding that I acknowledged. So probably the easiest way to understand why programmable hardware is interesting, because you could think of that as having the best of both worlds. You have the speed of hardware and the flexibility of software. Now, of course, if you're a pessimist, you might think you have the flexibility of hardware and speed of software. So that might not be the best device. Here's an example. This is actually not the largest device. And you could see that there are different kinds of computational resources, like the arithmetic blocks at the top, and then which are the coarse grain elements. And then there are deep level finding elements, which are also reprogrammable. And then there are also programmable memory blocks as well. So that you could see it is a fairly complex device, and the challenge is to make sure the user design works, but also monitor to make sure that it does. So, so the device I show you is called FPGA, and probably many of you have come across that. So the benefits are well known. You've got low risk because it doesn't involve fabrication. You could fix things after the design because it's very much like software. And then it's also runtime customizable, so we could actually change things during runtime. And it's actually been used in prototyping a lot of microprocessors and integrated circuits before they are actually fabricated. Now, perhaps there is one thing which is not so well known, which is that these hardware devices are also enable the modern internet because the largest usage is actually in the circuit switches or message switching. So if we do not have very fast message routers and switches, then the world might be a lot different from what we see today. So what are the design challenges? So we all know that these days it's unlikely that one would always start from scratch. Okay? So if we try to use design from somebody else, unless you get everything from Texas, otherwise there might be some bugs in there. So how can we be sure that they really work? Okay, so that's one of the questions. However, even assuming that we verify everything, we formally check everything, it might still not work in some circumstances because of the advances in circuit technology. The fabrication process get to a stage that is not possible to ensure that, for example, the same component on different locations on the chip would have the same timing characteristic. So there might be different depending on where your component is. And then, in addition, there would also be the possibility of aging effects, that it's literally running out. And of course, if you send these devices up to satellites, then there might be radiation effects that might also need to take into account. So one solution is, well, can we monitor them over runtime and see whether they do work as we expect? What sort of properties do we want to monitor? Well, obviously, there's the functional properties, which is well known, but there's also potentially one could try to get some statistical properties, and I'll actually explain later on why that could be interesting, and then also timing properties. And in addition, what we hope to do is to be able to provide a high-level description of such assertions so that we do not need to handcraft the elements all the time. And we could optimize them and make sure that the clear description can be optimized to an efficient one. And then another requirement is to make sure that, because we are now monitoring the user design, we'll need to make sure that the monitoring elements themselves would have to be have the same speed as the user design. Otherwise, if it is too slow, then you cannot achieve what one wants. And also each time, if we need to modify user design, that might mean long compilation time. So are there ways to address that? And then, of course, remembering that what we also hope to do, because we are monitoring user designs, we hope to be able to minimize the use of resources on the chip itself. Can we minimize the area that we need? And indeed, could we get it down to zero? Zero overhead, is that possible? Well, one possibility is that, remembering that because in this case, we are implementing designs on programmable logic, which comes from a lot of elements, and in many cases, not all of them would be used by user design. So as long as our monitoring circuit would only use the spare resources on the chip, then that could be seen as not making use of any resources that the user design will occupy. Okay. So what we hope to do is to introduce a new circuit, which is the monitoring circuit, in such a way that without modifying the user design. So what we are doing here is to allow the user design to stay where it is exactly, and then incrementally add the monitoring elements to superpose, if you like, to the existing user design. And as I said before, this process will only use spare resources on the chip. And then let's also remember the fact that that's the constraint that we want to make sure that the monitoring circuit itself will have to run at least at the same speed as the user design. So one way is to allow parallel processing so that one could effectively pipeline the connection from the places where we wish to monitor to the actual element that provides the monitoring circuit itself. Okay. So we develop a framework that allows us to automatically doing that. So I would not go into the details, but I'll just show you the results. And we found that indeed, if we do that, and we try some relatively large designs, like the Leon 3 processor, which has the Spark instruction set. And for example, we have some assertions to assert that the program counter is in the range of what we would expect. And we found that using this method of incremental compilation, we would be able to provide at least 4 times improvement in compilation time compared with doing everything from scratch. And in addition, this has the advantage that it will not disturb the user circuit, unlike some other methodologies that one might actually add the monitoring circuit to the source description and then recompile the whole thing, in which case the integrity of the user design cannot be guaranteed. Okay, so that's the means. Now, how can we develop the assertions and exceptions that will allow us to develop descriptions from a high-level way? So assertions are really relatively simple language. So the major challenge is make sure that the implementation needs to be very fast. And if we wish to support exceptions, then we will need to make sure that if there are any errors, then there would be facilities to address the control whenever the error happens. Now the challenge is to make it fast, but also to make it small, because remembering that what we hope to do is to only use the spare resources on the chip. So here are some examples of temporal assertions. So the purpose is to verify some runtime properties. And the particular framework that we follow is on pastime metric temporal logic. And an example would be if A happens, then B must occur in a bounded cycles, where A and B are any Boolean expressions. Obviously, one could make something more complex, but even a language of this sort can be, for example, used for verifying state machines, ProCoS, and other time-dependent behavior. And so an example could be checking a bus protocol, like PCI bus protocol, that the target must reply in 4 cycles, or otherwise there would be an error. And that could be written in a description like that, which I'll introduce here. And there are 4 expressions. Obviously, again, one could develop different ways of capturing what we want to monitor. So an example is the second one, which expresses the assertion that it is always true in the range A and B. Okay. So an example here is always true in range 0 and 3. So A is 0 and B is 3. Now, what would that be comparing to? So a implementation that we developed is look like at the bottom here. And I want to see that the way that it's being implemented is to replicate the input, delay one of them by 1 time step. And then the result is then replicated again, and then one of the branch is delayed by 2. And you could see that because this is conjunction, the first 2 give you 0 and 1 delay, which come up over here, and then the 2 will then apply to this one, give us the 2 delay, and then 2 and 1 will free. So that gives us the conjunction of 3 delays. So now one might wonder, if we actually have a bigger expression, what would that look like? And also, is this the most efficient implementation? Well, it turns out that if we have, for example, have a conjunction like those, one could actually develop an efficient implementation because that would only use resource N, whereas an obvious one with the delays at the top and then there is the conjunction at the bottom could actually give 2 to the power n. So how can we actually verify that the obvious one is can be efficiently implemented by the less obvious one. So one way that we develop verification is also based on relations, but is following the language developed by Mary Sheeran by capturing design as a binary relation. So we could actually use the mathematical definition of composition to describe the spatial composition of two blocks in series. And of course, we could then describe the replication of a series of elements and these spatial series composition inductively like that. And then even with very simple definition like that, one could already verify that given the case that an element D composed with R is the same as R composed with D, one could verify inductively that a series of D's followed by a series of R is the same as D and R replicated in series. Now, what could that be used for? That actually corresponds to the transformation I mentioned earlier, that if one regards D as a delay element or a register element, what it describes is that the D's can be distributed with the R together, so that the expression on the right-hand side corresponds to a pipeline version of the expression on the left. Once we have series composition, obviously we could have parallel composition, and that again could be defined straightforwardly, like I showed over there. And there is also the exchange law that could be very easily verified using the laws of relations. So, using this approach and with a few more operators, one could actually verify the design that I showed you earlier. So the obvious design starts from step A, and one could effectively be factorized by separating the delay elements, which are denoted by -1. So we could have this triangular shape elements of delay elements followed by the ends over there. And then one obviously recognized that this is an unbalanced tree, and one could do a balanced version of that over here. So there is this balanced tree over here. And then the next step is to split the big triangle of delays into that description. And then once we get that, one could apply the pipeline transformation that I described earlier in order to move that block of delay elements over here. And therefore, you can now see there is the block elements over here. And then the tree now moves into it. And then once we've done this step, one could then recognize that we have this block and this block the same. And therefore, one could then pull them out. And then what we would get would be that element over there followed by this one. And then if we now factor the ends, which are correspond to the S, together with the delays, we'll get the expression on the right-hand side, which is what we want to prove. Okay. So I don't put down the actual equations, because if I do that, then the diagram might become pretty small. Okay, so that's how one could verify some of the implementations. Let me provide the last example of assertion. And these assertions are trying to collect statistical properties rather than timing properties. So again, they need to run at the user design speed. And we found that based on the suggestion of our colleagues from Airbus, they found that that's actually been quite useful in some of the avionic instruments, which I'll explain in a second. So for the assertion language, the interesting addition is the possibility of computing the mean and the variance and so on of the signals, so that in case if the results are larger than what would be expected, then an alarm can be raised. So we actually developed various feedforward and feedback architectures or various algorithms. And here is an example that the yellow part would be the user design. And then we introduce these monitoring elements which compute the statistical properties. And if there's something goes wrong, then one could trigger a adaptive engine which will try to cause an alarm or reconfigure the design so that it will address the problem that it might encounter. So similar to what I showed before for the timing assertions, the implementation of the statistical assertion can also be optimized. That an obvious implementation would actually involve order n elements, and the efficient implementation could actually be order log n. Again, one could verify in the same way that I described earlier. How can it be used, or what can it be used for these statistical assertions? There's an example that I guess many of you have been traveling on a plane. Next time, if you are able to have a look, you might find that at the front of the plane, there are some tubes sticking out, and these are the pictured tube, which are used to measure the speed of the aircraft. Because remembering that once you fly above the cloud, it's not so easy to figure out how fast you are traveling. Now, the potential danger is that although these tubes have some heating element, they could still be frozen or blocked by ice and so on. And once that happens, then the autopilot will give up. And then if it happens that the pilots are not experienced, then it might actually risk the flight. And it did happen in some cases. In this example, what we did was the user design is actually computing the true airspeed based on some formula of assuming that the air is compressible. So that, for example, is given by this equation over here, which can be compiled into this data path. And then the additional monitoring would check, for example, the variance to make sure that if the variance suddenly become a lot larger, that might mean that the sensors might have failed, and therefore an alarm should be triggered. We also look at the resources used for these statistical assertions, and we found that in many cases the use of resources are relatively modest, especially after one transforms into the use of log n resources compared to order n resources. And we found that we could indeed compute the airspeed for that example within the hard real time limit. So, a quick description of current and future work. That we are looking at different kinds of tools that might help us to automate the implementation and indeed the verification, and indeed understanding different kinds of approaches that allow us to define the meaning of correctness within our approach. And in terms of different applications, we look at adaptive and fault-tolerant systems, and deciding where might be the best location as well as in time that one could place the assertions. And we think the approaches we develop could be used for different kinds of analysis, like analyzing pitches and so on. And perhaps there are possibilities of beautifying these hardware assertions with software ones. So, quick summary that we looked at different kinds of assertions, functional, temporal, statistical, and we look at ways of compiling this assertion decryption into hardware, and it could be optimized from order n to order log n. And we think there are ways to, for example, making only use of spare resources so that the results could be as optimized as possible. Thank you very much.
Are there any questions? Yeah.
You mentioned also aging of hardware, yeah?
Yes.
Can you expand on this aspect?
I think because the circuit technology getting smaller and smaller, it seems that the effects of aging might actually be getting worse. Some colleagues in our electronic engineering department, they actually did some experiments that they, obviously one could not, sit for 20 years and see what happens. So what they did is they tried to accelerate aging by hitting certain circuits and so on. Maybe in a way to accelerate the aging, and they did discover that certain failures could occur.
And your method would apply to this, that you, by assertions, you discover it? Or?
Yes, well, obviously, I'm assuming that the user knows what to look for. Okay. So in principle, as long as the designer knows what are the failure possibilities, then he or she could actually look for where that might happen, and hopefully do something against that. And indeed, it's possible that if certain regions seem to have a lot of failure, because the fabric that we use actually programmable, one could potentially migrate this area into somewhere else, which might be more robust.
Martin?
I was just wondering what class specifically of circuits, functionally speaking, are you looking at? Obviously, it's not a general purpose circuit, so it wouldn't be signal processing or so, because then you would have to check arithmetic, which would be hard to specify using temporal logic. So what class is it? Is it protocol circuits or?
Temporal, I think, protocol, and anything that might have timing-dependent properties. For statistical, I think that would try to detect things that might fail, so over time, that if you just look at a particular instant, then it might sort of work well. But over time, if you could see that the mean or the variance start differing a lot, then one would say, well, something seems to be going wrong. Because we have to provide the language for the designers, it's really up to the designers to specify what the failure mode and what he or she is looking for. So this is something that we do not say ourselves, but say, look, this is something you could use. What we provide are efficient means of implementation. Now, obviously, if one insists on only using spare resources, if you put too many monitoring in there, you will eventually use up. Okay. So there are different trade-offs that one would look at, depending on how robust you want the design, want to be. Because you could imagine that if it doesn't fail, then all the monitoring circuits are really not doing very much. So that is the sort of engineering decision that one would have to make.
Okay, last question.
Do you think that if the technology you suggested was put in place, we wouldn't have lost AF447?
I think it's very risky for me to say whether it will or not. All I would say would be that I believe that after that accident, Air France did replace all the filter tubes. But I think everything we could do to help, since I travel quite a bit, I guess if I do something, I might feel better myself.
Okay, so thank you very much.